So today I'm very excited to do this webinar about mid-latitude weather. We're going to talk about big low pressure system like the one I have in my background. So let's get started and I'm going to share my screen. So before we get into the technical things, I would like to let you know that this webinar, there is a written article talking about this same topic. So if you follow this URL, help.predictwind.com, you would end up to a collection called the Marine Meteorology course, and you will be able to find the mid-latitude weather article. But there are other articles like wind, clouds, sea breeze. During this presentation, I will refer from time to time to this article because there is some core knowledge that we're going to be using. So after this call, you can go and read those articles. Also, please note that those articles are available, of course, in English, but also in French, Spanish, and Italian. You just open the article and you can change the article language in the top right. So now let's get started. So the outline for today is the following. In part one, we are going to study the heat exchange at mid-latitude, which is what is driving the weather. In part two, we're going to recap and introduce what are weather fronts, and we will use this knowledge about weather fronts to understand the cyclogenesis at the surface. The surface, this is where we are all sailing, and this is where the weather fronts apply. But in part four, we will move up in the altitude to really understand how a cyclogenesis, how a low pressure system develop, because what's happening up there is very important. And finally, in part five, we are going to tie all of this together, and I will just present one slide, which is a cyclogenesis in 3 dimensions. So let's get started with the heat exchange at mid-latitude. First of all, what is mid-latitude? I have a colleague, Nick, and this is what he told me. He told me, Arnaud, mid-latitude, what are you talking about, Matt? So this is the opportunity to tell you the goal of PredictWind is to make complex weather simple and accessible to you, to all users. So I am going to use this philosophy all across this webinar. And whenever we introduce some technical words, we are always going to explain it. We're going to break it into bits that we can all chew and understand. And at the end of this webinar, we will be able to understand a complex topic. So by mid-latitude, I am referring to those colored areas. So those are the latitudes between latitude 30 degrees to 60 degrees, either in the north or the south hemisphere. And it happens to be where most of the humans are living. So you are probably living in the mid-latitude where you are right now. So for example, I'm talking about the US, Europe, or Japan. In the south, it will be New Zealand, the southern part of Australia, South Africa, etc. So an important concept that drives the weather in the mid-latitude is due to the differential heating on the globe. So all I'm talking about is there is more heating at the equator than the poles, like we all know. And this is due that the solar radiation is more intense at the equator rather than at the pole due to the shape, the circular shape of the Earth. And the consequence is that heat must be transported from the equator to the poles. And this creates an air circulation. And a simple analogy, it's a little bit like a room with a radiator. What do I mean? If I take a room and I am on one side where I've got the heat, the radiator, it's like being at the equator. This will create this type of air circulation. The warm air will rise. It will follow the ceiling of the room, which is like the top of the atmosphere, When you reach the other side of the room where it's colder, the air will sink. This is the North Pole. And at the end, at the bottom, at the surface, you will get a return flow. So this is a basic air circulation. And these concepts kind of apply to the global air circulation. But in reality, it's a bit more complicated due to the fact that the Earth is rotating. If you want to know all the details, please go to this article, which is the one about wind. I have taken from this article the following image. So this image is actually the real air circulation between the equator and the North Pole. As you can see, it's not just one cell, but there are three cells. But the main concept still apply. So if I am at the equator, I still have my heat, I still have my radiator, if you want. So it means that the hot and humid air is going to rise. And at the pole, I'm going to have my cold and dry air, which is sinking. And this is a polar high. And so you got this big cell, but of course, you got three cells because of the rotation of the Earth. What is interesting is what we have in the middle. In the middle, we have the mid-latitude between 30 degrees and 60 degrees. It's called the Ferro cell. The name is not that important, but what is important is in this cell, we are mixing the polar air with the equatorial air. So the air mixing is going to collide and is going to make complex weather. If you look carefully at this cell in the middle, you will see that the weather on the left is very different to the weather on the right, okay? On the left, you got a big cloud, and on the right, it's pretty clear. So what does it mean? On the left, we have what we call the polar front, okay? This is where the complex weather system happen, like depression or big lows, and this is the topic of today. On the other side, and an example, for example, 60 degrees north. This is, for example, the top of Scotland in the US. And as you know, it can be winter or summer. This place is always impacted by strong storms, lows coming from the west. But if you are on the 30 degrees north, this is, for example, the Canary Islands with the Azore High with nice weather. So once again, today, this webinar is focusing on this side of the Ferro cell. It can extend, to 40, 45 degrees, especially in winter. The storms go further south in the cell. So now I'm going to focus on the global air circulation just for the North Hemisphere. In fact, during most of this talk, I will talk about the North Hemisphere. I have just zoomed on this picture, just on the polar front. So what I mentioned before is because the Earth is rotating, it creates a force. We call it the Coriolis force. And the effect is going to deflect moving air to the right in the North Hemisphere. I have put here a little symbol of the Coriolis force. This is taken from our article, The Wind. But if you go to this article after this, you will also find a very interesting YouTube videos that explain in a very clever way the Coriolis force. You use a carousel, you put kids on the carousel and you make them throw a ball, and you will understand that there is a deflection to the right in the North Hemisphere, and also it's to the left in the South Hemisphere. What is the impact of the Coriolis force in this picture? So if I'm looking at this part, okay, the warmer air coming from the south, it's going to be deflected, and it's going to be deflected to the right. And it will happen to make this warmer westerly wind. This westerly wind, this is a wind, if you live in the UK, if you live in France, this is a dominant wind coming from the west. Same if you are in New Zealand, the main dominant wind are the one from the left. So this is it. However, on the northern side, because the wind is northerly, blowing from the north to south, it pushes to the right and it makes cold easterly wind. So now that this picture is clear, this is a cross section, I am going to represent the same thing, but in a 2D view. So we've got the polar front, and as we said before, to the south, we've got the westerly warmer wind, and to the north, we've got the easterly cold wind. So those two air masses need to mix, okay? Like the radiator, we need to mix the air to try to get some balance. And in order to mix, you can think about a big fan pushing warm air from the north to the south, and the warm air from the south to the north. And this fan, it's like a big low pressure system. It turns counterclockwise in the in the northern hemisphere. And this is the type of weather depression that all sailors experience when they are sailing across ocean at mid-latitude. For example, if you cross the Atlantic from the US to Europe, you will have those big fans turning counterclockwise. Of course, the fan is an image. So maybe the question you have is, how does a depression work? So I put here my depression, which is approaching Scotland. The mechanism of how a depression works is called cyclogenesis. So once again, cyclogenesis is a complicated word, but really, if you have to remember something after this webinar, is this big word just mean a big fan, which is mixing the cold air from the pole to the warm air further south. In order to really understand this depression, we need to have a good understanding of the weather fronts. So those are all the different weather fronts. You can already see them on the map. So in order to drill on how this system works, let's first jump into the weather fronts, which is going to be the part 2 of this webinar. So the definition of a weather front, it's just a line that separates two air masses with different temperature. On one side, you got the cold air, and on the other side, you've got the warm air. A very important point is to realize that at the front line, there is a big jump of temperature. We are talking a sudden change of 10 degrees Celsius, which is like 20 degrees Fahrenheit. For example, here we got 47 Fahrenheit, and we jump to 65 just by crossing the front. What are the symbols associated with the front, and what do they mean? The color obviously means the blue is a cold front and the red is a warm front. The symbols points in the movement of the front, like an arrow. So if I look at this front here, the spike, the triangle, give me the direction the front is moving to the right. And the front movement allows to define if it is a cold or a warm front. So the definition of the cold front is the cold front pushes cold air into warm air. So this is quite an important definition. So let's really drill into a cold front, so we all have a very good understanding of it. So as I mentioned before, this is a cold front, and the triangle give me the direction of the front. So it's moving from left to right because of the triangle. I know that the cold temperature is on the left and the warm temperature are on the right. Quite often people see this line and they do not make much out of it. But in fact, when you see a front like this, you can actually know the weather and the clouds that you have associated with this front. So this is the clouds associated with this front. Okay, the front is right here and the right front will be like here. And just by looking at this, you can know that you have big cumulonimbus developing right at the cloud. I'm not going to be able to go into details about all those clouds, but please go to the class number 3 about clouds so you can know everything about it. What I want you to take away is this thing. The triangle shape has a reason. We use a triangle to represent the sharp slope. I'm talking about the slope between the cold air and the warm air. And this slope, it's a little bit like two tectonic plates. Okay, they're gonna meet and one plate is gonna go on top of the other. Always the warm air is gonna go on top because it's less dense. But what is important is those triangles mean that the way the cold air do the rise and go underneath, it's pretty strong, pretty violent, pretty aggressive. And this is why it's a triangle. And this is also what represents the type of weather associated. It's sharp, it's aggressive. I'm talking about thunderstorms, heavy rain, strong winds. So please keep this in mind. If we jump now into the warm fronts, here again, the half circle show me the direction of the front. So I'm going to the northeast. I know that I have warm temperature on the left and cold temperature on the right. And once again, they are very typical clouds and weather condition associated with a warm front. And this is what it looks like. The takeaway is the half circle represents the gentle slope, how the warm air is going to move and go gently over the cold air mass. And also this is associated with the smooth and gradual weather that you have. The type of cloud, this is not cumulus, but this is stratus, and you are expecting constant rain, not heavy rain. After the warm front, we can talk about the stationary front. So the stationary front, you still have a cold air mass and a warm air mass on both sides. But in this case, those air masses are not moving. There is no interaction. And this is why we use both symbols pointing in opposite direction to represent no movement. And finally, the last front is the occluded front. So this front actually only has cold temperature on both sides of the front, even if one side is slightly colder. The two masses, even if they are similar temperature, they are still very different, okay? And we use this purple color to represent the front, and the symbol also points in the direction where the front is moving. So the front here is moving from left to right. And finally, a question you may ask is, when does this occluded front happen? Is it very unusual? Not really. It typically happens when the faster cold front catches a slower warm front. And more on this later on. Yeah, so in this picture, you can see it here. We've got the occluded front here, and this is a cold front. So let's say we wait another 2 hours. This little triangle will catch up this little half circle, which will extend the occluded front further south. So now that we have understood what is a weather front, we can apply this knowledge to understand cyclogenesis, how it works at the surface. So cyclogenesis is just a big word that defines a conceptual model of how a depression forms and develops throughout 5 stages. Remember in part 1, we mentioned the big fan. If you have to take anything out of it from this webinar, is really a cyclogenesis, a depression, just works like a big fan. I think it will be a good takeaway, which is just mixing the cold air from the north with the warm air from the south. Cyclogenesis will bring now some science to explain this image of this. So let's go into stage 1, which is called equilibrium. So we are at the polar front, 60 degrees north, and we have what we discussed before, a cold easterly to the north and a warm westerly to the south. And because those two air masses are in equilibrium, they are not interacting with each other, we can use the stationary front. I have represented this, I have represented this in this format, okay? The same thing. And what is interesting is when you see a flow like this, going to the left and to the right, you can already understand that those two flows, they are in equilibrium, but they really want to start a rotation. And you can imagine those two flows like two hands holding a pen in the middle, and you can feel that those two flows want to make the pen in the middle rotate and rotate counterclockwise. This is what will happen in stage two. So stage two, this is the formation of the low. This is a very important stage. So what happens? In the atmosphere, there is always some disturbance, okay, which is going to change this. You can call it a polar wave. But what does it happen? What does it make? This disturbance will push the cold air to the south, which creates the cold front on the left. And the disturbance will push some of the warm air to the north, which creates a warm front. Those two fronts, as we've seen before, they are associated with rising air, and also air pressure drops under the fronts. And the point where the cold front and the warm front meet is where the pressure dropped the most, and this is the center of the low. The stage three is a development of the storm. So I've put here a big fuel pump. Maybe you wonder what I'm doing. This fuel pump represents the fuel, the energy available. There is another word to refer to this area. We call it the warm sector. This is where the warm air of the low is located, but this is really the fuel where the energy is coming from. How does it work? This warm air is going to rise either by this front or this front. When it rises, it cools down and it precipitates. And as you guys know it, when there is precipitation, there is a release of energy when you go from a gas to a liquid. And this release of energy will help the system develop. It will make the low deepen. It will create faster wind at the surface. It will also create more air rising, which will lead to more precipitation. And you know what? More energy being released, which is just a loop. And this is a development phase of the storm. Then we get into stage four, which is the maturity. So as we mentioned before, the cold front is starting to catch up the warm front. And this is the beginning of the occlusion that starts from the center of the low. What's interesting is right here, what's happening is you've got the warm air is being squeezed. Okay, you don't have any more warm air, and by being squeezed, you can realize that the warm air is actually rising, and there is a lot of precipitation, intense rain are happening in the occlusion front. And the warm air sector is still here, but as you can see, it's decreasing. So when you start having occlusion, you can say this is a maturity, this is a beginning of the end of the system. And this is what we get in the last phase. This is a dissipation, okay? The occlusion is just advancing, using all the energy, and we just end up with very little fuel left over. And what will happen is the storm is going to die and gradually disappear. So I hope this conceptual model is clear. This is really a concept. In reality, of course, it never really happened like this, but it's very good to have some understanding of this concept. Now, like most of my teammates, like Karen, they live in the southern hemisphere. And when we show them, this low pressure system in the north turning counterclockwise, it's not very natural for them to understand. So I tried online to find a cyclogenesis for the South Hemisphere, but I was not able to find those pictures. So I've done a trick for you. So what's important to know in the South Hemisphere? The pole, the South Pole, is to the south of the equator. So it's upside down. The Coriolis force is also inversed. So in order to create this cyclogenesis picture, what I did is I first flipped the picture to reverse the position of the pole. And then I mirror the image in order to change the rotation. And here is how it looks like. So as you can see, we've got the warm air to the north and the cold air to the south. But importantly, the wind is still blowing is still westerly warm wind. I hope this is clear. Then in step two, we can see the beginning of the storm. And the interesting part is a clockwise rotation. And this is, you can see stage three, which is mature. For example, I put the fuel, but of course here, the fuel is toward the north, toward the equator. And of course, the rotation of the system is clockwise. And finally, the dissipation. I hope this does not confuse the people in the North Hemisphere. Myself, it's not natural to look like this because I live in Europe. Now that we have covered the cyclogenesis at the surface, which is in fact the most important, we are all sailors, and this is a type of maps that we look at the front, at the isobars and all this. This is all good, but if you really want to understand how the system works, you have to look in the altitude, because in the altitude, you will find favorable conditions that, if they are met, can make a storm really, really powerful. So let's dive into it and let's move up into the atmosphere. So here I'm using the analogy of a chimney to represent both the atmosphere, but also the structure of the storm, of the low pressure. So we can divide this into three levels: the surface, the mid-level, and the high level. And I put here the millibars, which are standard: 1,000 millibar, 500 millibars. This is the standard middle of the atmosphere. And 250 millibars, you are almost at the tropopause, almost at the top of the atmosphere. So here, for this chimney to work, and the chimney, is just a metaphor of the air rising at the center of the storm. For this to work, you need favorable condition. What do you need at the surface? At the surface, we already see it, but we need to have the fuel. So we need the warm air. What you need is you need to have air rising. We already see it. The air rising comes from the front, but it also comes from the low pressure. At the center of the low, the air is converging and the air cannot go down through the ground, so it goes up. So those are all the good ingredients that you need to have a system forming. But if you can have interesting features at the top, it will also greatly help the system develop. So in the middle, at mid-level, what you want is you want the air to keep rising, keep alimentating the rising. What you need is you need instability, or in other words, will be vorticity. And we are going to go into this later on. And finally, what do you need at the top of the atmosphere to help the rising? What you need is called divergence. Divergence is just a word that means that you need to have the air evacuate, okay? Evacuate the air, allowing more air to be pulled up. And this divergence at the top of the high level is a key feature. So once again, the cyclogenesis at the surface versus the altitude. If in the altitude you have no favorable condition, the depression is not going to develop much. And you can think about the chimney will choke. But if you have favorable conditions in altitude, the depression will develop, the low will deepen, and you will get a powerful storm like something like this. Here, every ingredient is lining up: surface, mid-level, and high altitude. So I could stop here and just tell you that you need favorable conditions in the altitude, but I want you to take you deeper into this and get some real understanding of what's happening in altitude. So to do this, we're going to briefly talk about weather map in altitude. They look a bit different than at the surface. So at the surface, we talk about isobars, but in the altitude, we talk about geopotential height. And a geopotential height just means the height of a pressure level. For example, the height of the 500 millibar level. Another difference is when you are in altitude, we don't really talk about low, we talk about trough. Instead of talking about high, quite often we talk about ridge, just different words. But to simply put it, those upper level map of geopotential can be viewed as a topographic map. Okay, we are just looking at the height of the pressure level like this. To explain it further, if I just look at a trough, okay, a trough is like a valley, the low is the bottom of the valley, and the axis, which is called the trough here, this is the line. If you will be walking to the L, it's like walking down the valley. The ridge is a similar concept. If this person is walking up the ridge, he's just walking up and he has two cliffs on each side. So now we got this basic concept. We can apply it. The reality is trough and ridges, they come together. So here is the map. This is a mid-level map, okay? You can see it because, you know, those lines are very smooth. There is no impact of the mountains. So this is a mid-level map. What is nice also when you look at this middle map is we need to realize that at mid-latitude, the wind is always blowing from west to east. So you got the arrows here, but all those lines, the wind is just blowing from the left to the east and doing some turns as well. So what is interesting here? The trough right here is always associated with bad weather, okay? And cold air. The ridge right here is associated with high pressure, nicer weather, and warmer air. And something you may realize is, first of all, there is a wave pattern creating between the trough and the ridge. But the most interesting part, and maybe some of you notice it, is the worst weather is always on the right side of the trough, you know, like here, and always like here. And the reason is because you have very favorable conditions in altitude, always in these pockets for the storms to develop. So let's study why always on the right side of the storm. But once again, if you need to remember something from this, just remember the right-hand side, the downstream side of the trough is where you have storms developing. And the reason why is because in those areas, the air is rising and is diverging in altitude. And let's study this further. So now we're getting into the real stuff. So this is a map of the geopotential map at 500 millibars. You know, when forecasters look at this, they are not looking at every lines. What they are looking are center of actions. There are some parts that are more important than others. So I put it here. This is the center of my trough. And here I'm putting the trough axis. And here I'm putting the pocket. This is a pocket where the area is rising and the worst weather is. Once again, I want to take you deeper into these things, and we are just going to understand just why those black lines all stacked to each other and pointing to the northeast, why this is a sign of air rising. So let's get deep into this. In order to do this, we need to introduce a concept, which is vorticity. Vorticity, it's a big word, but it just refers to the spin of the air, only this. And there is a link between the vorticity and the rise of the air. To explain this, we can use an analogy. We are going to use a skater analogy. So this skater, she's turning. And as you all see on TV during the Olympics, when she's going to bring her arms together, she's going to naturally spin faster. The physics is there is conservation of the angular momentum. And this thing can be applied to the air. So think about an air column spinning like a skater. This is it. If suddenly my air parcel, my air column spin faster, the column, has to stretch. It needs to be narrow, like the arms bringing together. And the result of this is going to be a rising, the stretching of the air parcel, which leads to the rise of the air. So, of course, this is just an analogy. Something else to understand is the vorticity can be positive or negative. In our case, we are only wanting positive vorticity because positive vorticity means rising of the air. And this is also linked to a counterclockwise spin. Negative vorticity will be the other way around, and this is sinking motion. And this is not what we want in a storm. So we want the air to spin like this in order to have rising in the North Hemisphere. So this is what I was saying. Negative vorticity leads to air sinking, and this is what you have on the left of the trough. Okay. And finally, I want to tell you that there are three types of vorticity. We've got the curvature, we've got the shear, and we got the earth. Let's go briefly into these three so you got a feeling of what it means. So let's start with the curvature vorticity. As I said before, it can be positive or negative. In our case, we are only going to look at the positive vorticity because we want the air to rise. So as you can see, if you've got a curvature that is counterclockwise, this is curvature vorticity. So this means that everywhere in the trough, we are turning like this to the left. So everywhere here, we've got vorticity. So there is some rise everywhere in a trough. So this is a good reason why we have storms develop in a trough. The second thing is the shear vorticity. When is it positive? Is it positive when the wind increases speed from the low? Maybe you can feel it. This thing wants to create some spin. So the answer is when the isobars are very close to each other, when they are stuck to each other, it creates a lot of shear in this area. So that's why we are in the pockets. And finally, where we have the Earth vorticity is when you have air going from the south to the north. You are going to higher latitude and the Coriolis force increases. So this is the final thing, is on this side of the trough, the air is going from the south to the north, and it is positive vorticity, while it's negative. So for all these reasons, now you understand why this area has a lot of positive vorticity, and this will create perfect condition at mid-level to have the air rising, which is the middle of the chimney. Now that we have understand the mid-level, I want you to take you to the high level. We are at 250 millibars, which is 8 kilometers high, so very high in the atmosphere. So here we're going to introduce the jet stream. I think everybody has heard this name, but quite often it's hard to really know what it means. So the jet stream is a fast-moving river of air flowing from west to east all around the world. And it goes quite fast, up to 150 knots. I put here a picture. So this is the river of very high wind speed. And if the jet stream is associated with divergence, the evacuation of the air, then it's going to pull the air up at upper level. And this is very, very favorable condition for depression to develop at the surface. Quite often, you can see people, weather forecaster on TV. They show some low system in the Atlantic, for example, and they are not big, 1,000 millibar. And in a couple of hours, 12 hours, the system can intensify very rapidly. The pressure will drop and wind at the surface can reach 30, 40, 50 knots. This is typical that the jet stream had some interaction and the divergence helped the system accelerate. My question now is when you look at this, where do you see the divergence in this picture? Okay. And the answer is not very simple. Divergence means the air goes away, but it's not easy to look at this and see the divergence. So come with me and we're going to study and see where you have divergence in such a flow. So the jet stream around a trough looks like this. So I already give you the answer. On the left side, you've got the convergence, and on the right side, you have the divergence. And as I said before, the divergence is what we want to have the evacuation. But really, if you look at this, me, with my eyes, I cannot see the air diverging, but there is. So let's take an analogy. After the skater, let's take a car analogy. So when cars goes into a left turn, like this one, first of all, they will slow down and they will tend to converge at the entrance. You can already see them, with those tire tracks, they converge right here. And on the exit of the curve, the cars will accelerate and they will tend to diverge. Maybe you can see some of the tire tracks that are starting to diverge. So as I said before, we have divergence here. And this car analogy is just to give you a feeling. Okay, the atmosphere, this is more complicated because we have right turn and left turn, and they behave completely differently. But I think this is a good way to remember that divergence is at the exit of the trough, which is a left turn. In order to really understand why you have divergence here, we need to answer two questions. The first one is why the left turn creates deceleration and then acceleration, and why the acceleration creates divergence. So let's come with me and let's answer those two questions. So why the left turn creates deceleration at the entrance? Okay, so here I'm taking the jet stream. At top of the atmosphere, the low pressure is to the north, the high pressure is to the south. The jet stream is going in a straight line at 100 knots. There is equilibrium. At this altitude, there are only just two forces. The first force is the pressure gradient, which is directing from the high pressure, which is deflecting to the right in the north hemisphere. And there is a balance, and my air is moving happily in a straight line at 100 knots. But what happens when my particle enter a left turn? The pressure gradient will not change. The high pressure is here, the low pressure is here, so the pressure gradient is unchanged. A new force will happen in the turn. This is called the centrifugal force. This is the same force if you are in your car. If you take a left turn, your body will move to the right side. outside the curve. But you still need to have balance. And in order to have balance, the Coriolis force needs to be less. Okay? So those two vectors equals this one, it's equilibrium. But the big difference is the Coriolis force has decreased. And because the Coriolis force is directly proportional to the speed of the air, the consequence is to have lower wind speed in the turn. Let's say 80 knots. So you have 100 knots at the entrance in a straight line, 100 knots at the exit. So clearly you have a deceleration, but most importantly, you have acceleration of the wind when you are exiting the trough. So we have answered this question, number one. And number two is why the acceleration creates divergence. So in this plot here, maybe you cannot see it, but this is a slow wind speed, and there is my acceleration. So I have added this to really show that there is acceleration here. And the acceleration of air particle is going to stretch them apart. And it's going to create an empty space. If I use the same car analogy, if you are stuck in traffic, not going fast, and suddenly cars are going to move fast in front of you, it's going to create some space, empty space. This is exactly what's happening here with the air. And this empty space is divergence. It doesn't look like this, but it is the same. There is empty space. And because there is missing air has to come from somewhere. We are at the top of the atmosphere. There is no air coming from here, from space. So the air is going to come from below and the air is going to rise. So now we understand why at the exit of the trough, you have divergence. I'm going to finish by this, but by showing a real picture of the jet stream. So this is a jet stream. Quite often we are only looking at the jet streak. Jet streak are the places where the jet is really fast. I'm talking 200 knots, okay? And the jet stream is in a trough. And then I said before, at the exit, and especially at the left exit of the jet, this is where you're going to have all the divergence. And if you happen to have a low pressure system at the surface, this left exit will greatly enhance the storm and make it into a powerful storm. All right, so I hope everybody has followed this thing. I know it's been quite challenging. So let's finally see the last slide, which is going to be a summary combining everything at the surface and in the altitude. So this is the 3D view. So if I look at the surface, I have my low pressure center, and I've got my warm front and my cold front, and it's spinning counterclockwise in the low level. This arrow represents the vertical motion of the wind. This is a mid-level. You have a lot of vorticity that help the rising. And at the top, you have the jet stream. And if the divergence is exactly matching the center of my low, those are perfect conditions. So some things to remember is the low on the surface is always a little bit ahead of the axis of the trough, just because the divergence is on the right side at the exit. So I hope you will remember this picture, which really is a beautiful summary of the cyclogenesis in 3 dimensions. Thank you very much.
Thank you, Arnaud. That was absolutely amazing. I can see that you've put so much effort into that whole presentation. You've done an amazing job, and lots of comments online about, thanking you for your work and for the information, for the learnings. There's a lot to take in there. And so everybody that registered, we had over 4,800 people register for this, which is amazing. Everybody will get an email from me with the recording, so you can watch it. If it's anything like me, I'm going to need to watch this a few more times before I completely understand all of it. So that will come out probably tomorrow to everybody. And I'll also link in the other course links so that you can go and look at the other ones. So this course is a series of, is it 5 or 6 that we did? I know.
6 in total.
Yeah. And so we've made that free to everybody online. So we're not here to try and make money out of you on this course. This is all about your learning, understanding so that you can be safer on your boats. So thank you for that. There was a lot of really good questions, some that I can't answer and that I'll ask you after the session, Arnaud. But there was one from a customer, Jacques. It seems that for some time now we're experiencing in the French Atlantic and the UK and Ireland much more persistent easterly winds, northeast, southeast, versus the traditional westerly flows during the spring and summer. Do you think that's perception or reality? And if it's true, is there a reason for this, do you think? That's a curly one for you?
Yeah, like it's a very broad question, you know. Of course, you know, when we are telling that the westerly warmer wind at mid-latitude, this is a predominant wind, but it doesn't mean that on any single day you're not gonna have a different weather system. Um, I have the impression he's talking about the spring and the summer.
Yeah,
What is true is, you know, when during the summer in the North Hemisphere, okay, so polar fronts will tend to move further north, okay? So those big weather systems, they're just going to move further north. So summer will be a moment where you will tend to experience more easterlies than the winter. So this is going to be my answer. In terms of this particular year, I do not have any specifics. Global warming may be playing a role. I'm not sure.
yeah. And one that we get asked a lot in the support team and in general is, which model should we be looking at? Is there one that's better than another? How do you decide which one to choose? Do you want to just quickly talk about our multi-model approach and how to do that?
Yeah, so I think, you know, it really depends on the type of forecast you want. If you are a day sailor, okay, and you want to schedule today or this afternoon sailing, me, I use very high resolution model like and regional model that only forecast for a certain part. So PredictWind, we offer PWG and PWE 1 kilometer. So those are high resolution and they are just calculating the forecast just for your area for the next 48 hours. If you are in Europe, for example, you can use Arome or you can use Icon also that are good regional model because they have the highest resolution, they really capture sea breeze effects, the coastline, the geography. So this is what I use for the very short term. But then when you want to look more ahead, 3, 4, 5, 6, 7, 8 days, you need to look for a global model. A global model forecasts the weather all over the world. And me, typically, I like to use ECMWF, a 9 kilometer, which is a good one. But we also offer GFS, which is an interesting model. We've got also UKMO. So this is what I use. So for sea breeze, local thing, high resolution. For big weather system ahead of time, I like to use global model.
Cool. And I noticed you mentioned Icon there. So just so everybody knows, Icon is coming into PredictWind within the next couple of weeks. We're just in the process of adding that now. And we've just added the AIFS, the ECMWF AI model as well, which is rating really well. So we're always evaluating, what models are best for the company and for our customers, and trying to always provide you with the best models that we've got. So you'll see some changes coming in the next few weeks, and that's pretty exciting. We're looking forward to adding those. So yeah, I think we'll
Yeah,
wrap it up
definitely.
there. Oh, sorry, go on.
Definitely. And also one last point, you know, if you are watching from North America, we have also two very high resolution weather model for North America, which is HRRR and NAM. Okay.
Yeah, cool. All right, thank you. So yeah, once again, if there's any questions that come out of this that you have, you can email our support team, just support@predictwind.com. You'll get through to our AI bot called Finn first, but if you ever have questions that Finn can't answer, just tell them that you want to talk to a person and you'll come through to one of our awesome support team who are all sailors, so we all know what's going on out there. Arnaud, thank you for an amazing presentation. I loved all the pictures and imagery and examples that you used. It makes it really possible for people like me who are, don't understand a lot of technical stuff to really comprehend the what it's like in real life. So really appreciate all the effort you've put in there, and thank you. So yeah, we look forward to seeing everyone in the next session, which will probably be in about, I don't know, 3 or 4 weeks, couple of months' time. Another one before Christmas for sure.
Thank you, everyone. Bye-bye.
Thanks.